Log on, tune in, find out. Another good idea from Cambridge.
Okay, today I'll start by talking about stacks. So recall that yesterday I had defined category fibered and groupoids. So where S is the base category, which, for us it's mostly going to be the category of schemes. This is the category of all the parameter spaces, and then X is the category, so this is the category of parameter spaces for families, and X is then the category of, families of a certain type, which I call X families. And the axioms for CFG formalize the notion of existence of pullbacks. CFG says that families can be pulled back and are unique, so families can be pulled back or restricted. And so let me just, I want to start out to explain the next thing with this example. So example of such a thing. So vect sub n, so this is the CFG of vector bundles of rank n. Right, so the objects of this category vect n are such things. So E over S is a vector bundle over the scheme S, and morphisms are morphisms of vector bundles. So if I have a morphism, if I have a vector bundle over S and another vector bundle over another scheme T, a morphism is a commutative diagram. Such that this is a morphism of vector bundles, which implies that it's going to be, I guess I should say it is what this means is that this map induces an isomorphism of F with a pullback of E to T. So it's a Cartesian diagram. And the functor to the base scheme is just forgets the vector bundle, right? Maps the vector bundle to the base, or maps the morphism of vector bundles to the morphism over which it lies. And so this is a CFG. So the fact that this is a CFG expresses the fact that I can pull back vector bundles, and the pullback. So CFG can pull back vector bundles and pull back is unique up to unique isomorphism. And it's convenient to choose for every category fiber in group, just choose at random a pullback for every single object, and every morphism to the base, choose a pullback. So that just makes a lot of things easier to state and to think about. And like, for example, well, for this category of fibrant groupoids, there is someone has at some point actually constructed a pullback, and well, we can choose that one. Yeah. Depending on your construction of pullbacks, you get different ones. Anyway, so but that's not the only thing about families of vector bundles. Actually, more interesting is that we can also glue families of vector bundles. So families glue vector bundles. I mean, I think of vector bundles as families of vector spaces, right? So this is a vector bundles, families of vector spaces. I can glue families of vector spaces because, vector bundles can be glued. So, this I'm going to write down what this means explicitly, precisely. So if I have I'm going to work with étale covers. So if Si to S is an étale cover of the scheme S, and I have two vector bundles over S, ES, FS. Vector bundles, or families parameterized by the same base scheme. And I have isomorphisms. So between the pullbacks of the two bundles to Si, such that for every pair ij, the restriction of phi I to Sij, which is the product of Si with Sj over S. So this is equal to phi j as isomorphisms from E restricted to Sij to F restricted to Sij, then there exists a unique phi from E to F such that phi restricted to Si is equal to phi I. So this means, this is the fact that I can glue isomorphisms of vector bundles. And the second one is that I can glue vector bundles themselves. So again, if I have an étale covering, and I have vector bundles over each of the Si. These are vector bundles. And then I have isomorphisms phi ij from Ei to Ej. So Ei pulled back to Sij, Ej pulled back to Sij. So these isomorphisms on the overlap such that the co-cycle condition is satisfied, so that for all ijk, phi ij, and then phi jk is equal to phi ik. This is happening over Sijk. Then there exists an E over S and phi I from E restricted to Si to Ei such that, what's this, so phi I and then phi ij is equal to phi ij. Okay, so, and I should remark, if you just use the risky covers, then yeah, well then this is just standard theory of vector bundles. But in general, for étale covers, you need descent. So use and this uses descent theory, as it's known, using the fact that that okay, so I can remark. Well, I didn't write it, but I said that all morphisms of vector bundles are such that, so this means such that F is isomorphic to E restricted to T. So I don't ever admit anything but isomorphisms. Is because I want to, think of this as a category fibered in groupoids, where I mean, if I would include more general morphisms, it wouldn't be a category fibered in groupoids. I mean, the uniqueness of I mean, essentially the axioms of CFG prove that this kind of diagram has to be Cartesian. So so it does say Cartesian there, right? Yeah. So this Cartesian means that thing. So all of these things are automatically isomorphisms in this definition. And because of that, these two axioms make sense as they are written. Well, okay, instead of vector bundles, say X families. So these two axioms for every CFG over the category of schemes. Or, and more generally, or they make sense for every CFG over some random category, as long as we have a Grothendieck topology on it. And the Grothendieck topology just means that you know what a covering is. And so in our case, the Grothendieck topology is the étale topology, and a covering is an étale covering. So a bunch of étale maps such that the union Si to S is surjective. That's an étale cover. And so definition. So if that's a stack. So if X satisfies these conditions, it's a stack. If it only satisfies one, then it's called a pre-stack. Right, and so other examples of categories with Grothendieck topologies, for example, you could take analytic spaces differentiable manifolds, and covering in these two you can take usual notion of covering. Or the étale topology. In these cases, it amounts to the same thing because every étale morphisms has local sections in those categories. Okay. So let me just give you an example. So, for example, m bar 1, 1. This is the so this is the CFG of such diagrams. So C over T is a flat projective family of curves of arithmetic genus equal to 1. So all fibers have arithmetic genus of 1. There's a flat projective family. And P is a section. This is a stack. Because you can glue flat projective families, so just like you can glue vector bundles, and that uses that you can descend projective schemes. So this again descent theory, but I mean, yeah. Okay. Okay, another example of a stack. So let's take an algebraic groupoid and assume that this diagonal map from R to U times U, the source map and the target map, is quasi-affine. And then define I don't know quite what notation is best. Last time I used this notation. This is slightly shorter. U over R in square brackets. So this is called the category of torsors for that groupoid. So let me just describe the objects. These are pairs. So objects. So I have a morphism of schemes. This is a morphism of schemes with étale local sections. So étale locally in T, there exist sections of this morphism. And then I have, this banal groupoid I get just by taking the fiber product of P over T from this groupoid to the given groupoid R to U. So this is a morphism of groupoids. But it's not a random morphism, it's what you could call square morphism of groupoids, which means that these diagrams, either if I take the source maps or the target map, in either case I get a Cartesian diagram, a pullback diagram. those are square morphisms of groupoids, as opposed to morphisms of groupoids. Right. Okay. Such pairs are torsors parameterized by T. And okay, you can pull these back. If you have a morphism from another scheme S to T, you can pull back P to S, and then you get an induced square morphism of groupoids. That's easy to see that this is a CFG. But to prove that this is a stack, you're going to need to glue these kind of torsors. So if you have them giving, well, just like over there, over a cover of T, you have to construct a global one over T. And for that, you need a descent theory for these groupoids. And descent theory, you need some assumption. And this quasi-affineness of this assures that to prove stack axioms, you need so if you want to drop this assumption of quasi-affine, you have to work with algebraic spaces instead of schemes. But let me not do that in these lectures for simplicity. Well, then if you replace your whole category, base category S, with a category of algebraic spaces, and then you have descent theory all works without assumptions of quasi-affineness all over the place. So then it is I didn't, but I'd leave it as an exercise to figure it out. It's, it's like, it's not. I mean, these are not very intuitive objects. I mean, it's just mostly a technical thing too. Let me give you an example. Before I do that, let me. Just if you are actually interested in a proof. So I don't know if I've ever mentioned this. There's notes by Kresch. Of like some beginning first chapters of a book on stacks. And so if you Google these words, Kresch algebraic stacks, you can find these notes. And you can find all these kind of things proved there. Okay, another example. Where these things, these kind of torsors are much easier much more intuitive because you're more used to what goes on. So if you have a transformation groupoid where, say, G is an affine algebraic group, and probably X has to be quasi-affine or something, then this condition is satisfied. So if you work out what this definition is in that case, it's equivalent. So a torsor over T is a pair. So P T over T P to X, where this is a G torsor, a principal homogeneous G bundle in the usual sense, and this is a G equivariant morphism. So if there's my transformation groupoid, and here's my torsor over T, and well, okay, now I've written this. You can see that this, you can convince yourself that this equivariant morphism is going to give rise to a morphism of groupoids from this transformation groupoid to that one. And then because this is a torsor, G times P, this is actually equal to the fiber product. And you can see that this kind of data gives rise to that kind of data over there. So, so in this case, these things are quite easy to work with. Just G torsors with an equivariant map, and this is just generalization to groupoids. And whenever you can't figure out what goes on here, then you go to this example and work it out here and translate it all back into that language. Okay, so next, so I have to define what is the fiber product of CFGs. Okay, so let's say we have a diagram, X, Z, Y. So these are all CFGs, all over the same base category S, and all these morphisms. So these functors of these categories, they commute with the projections to S, commute strictly with the projections. Okay, so the fiber product so what is this? So the objects are triples X, phi, Y. So where X is an object of X, Y is an object of Y, and phi is a morphism. So from f of X to G of Y. So I have an object here, an object there. I map them over there, and there I have a morphism between them. In other words, an isomorphism, because all morphisms. And so, well, all this over the same S in the base. So X and Y lie over the same S, and this morphism lies over the identity. Morphisms. So you have X these are pairs, let's say alpha beta, where just try to. if I have a morphism in x alpha to x prime, that lies over some morphism in the base, s to s prime. And this one has to lie over the same one. So that's a pair, such things. Okay, such that. A diagram commutes, if I map everything to z, so there's f of x. F of alpha, f of x prime, and then there's g of y, g of beta, g of y prime, f of x, there's phi, and there's phi prime. That's just the natural notion of isomorphism between such triples. So if you have a diagram of CFGs, W, Y, X, Z. So that means you have all these morphisms of CFGs. You have this composition and that composition, while this double arrow means you have a natural transformation from this functor to that functor. If you have such a diagram, you get an induced morphism of CFGs over S from this W to the fiber product. You can convince yourselves of that. And if this is an equivalence of categories, if this is an equivalence of categories, then the original diagram is called Cartesian. Then some people say two Cartesian. Because really it's all happening inside the two category of categories. There's all these categories and there's natural transformations in the picture. One of the main applications of this notion for us is what do I want to say? So if I have an object of a CFG X sitting over the parameter scheme S, and whenever you have an object that induces a morphism from the base scheme to the CFGX. Whenever you have a morphism T to S, you just map this so T to S goes to X restricted to T. Because you've chosen all of the pullbacks, this defines a morphism. So you can form this diagram, and then so you can form the fiber product here, which maybe I'll write isom XX. And so Excuse me? Oh, I keep changing between S and U. I'm sorry. It's always. Thank you. And so if I this fiber product means I have an object here and an object there. Those are essentially, think of them as points of S. I have 2 points in S, meaning I have 2 different members of the family, and then I have an isomorphism between those 2 members over here. So the set of triples, as I defined it up there in this after contents, is exactly the same thing as a symmetry groupoid as I defined it yesterday. So this is so if this CFG, which I've defined over there, is representable by some scheme R, then I get an algebraic groupoid, which is the symmetry groupoid of that object. Okay, this makes this definition of symmetry groupoid work in arbitrary CFGs. It makes it okay.
Can you explain which part of that is a definition and which part is a statement?
There is no statement, it's just a definition. So if, okay, so this, so I define the CFG, which I've denoted isom XX, to be the fiber product. And if this CFG is isomorphic to R for some R, so in other words, if it's representable, then this RS is, well, maybe there's a statement here, is an algebraic groupoid, and then it's called. More precise. Okay. Okay, so I already had this definition last time. I'll write it down again. Be slightly more general. So X. So this is so assume I have an algebraic symmetry groupoid of this family X over S. Then so if this is so the family is defined to be versal if these maps, source or target map, either one, its equivalent, is smooth.
Is the isometry CFG defined there? Is it defined over the original base category or over the schemes over S?
No, this is everything happens over the same base category all the time. So these are all CFGs over S, and this is also over S.
So isom X.
This is again a CFG over the category of schemes, and if it's representable by some scheme, then yeah. So if I have some other family Y over some other base, oh God, this is not, can I ever, So I started with S, so now it's T. If every X helmintine is locally induced from the versal one, X over S, so that means there exists a cover Ti to T, and so there exists a cover, and there exists T prime to S such that Y so I can cover T with such T primes such that if I pull back Y to T prime, then that is also pulled back from X. No, this is 1 is versal and 2 is complete. Yes. And so then there's the and then there's a theorem which is just a formality actually, but suppose X over S is a stack, and suppose R to U with quasi-affine diagonal if this is a symmetry group of a complete versal family. Okay, so now I'm back to U. Then I have a morphism of CFGs over S. So, so if some family, say Y over T, I map that to so I pull back Y, which is over T, to the product T times U. And I can also pull back X, which lives over U, to T times U. And then I can consider all these isomorphisms from that family to that family, which is over T times U, but I just think of it over T. Well, part of the claim is that this is then actually a torser for this groupoid, right? So that this, I can write this down. This thing is a torser for that groupoid. But not only that, this functor is an equivalence of categories, and this is and rather than trying to explain the general proof, I'll just do an example. Let's say X is the vect n again, so just the stack of vector bundles over let's say for simplicity, this is schemes over the complex numbers. So star is the one-point scheme, spec C. I just take the trivial vector bundle, which is Cn, the vector space, or this vector space is a family, is a vector bundle over the point, right? And this is a complete versal family. Well, it's the symmetry groupoid is just a group, GLN to C, and so all the conditions are satisfied. So the symmetry groupoid is smooth, and it's a complete family because every vector bundle is locally trivial. Right, so what I've wrote down over there, and this up there under 2, in this case, just says that every vector bundle is locally trivial. And so this is a complete versal family. And then this theorem says that the stack of vector bundles of rank n maps to, this is a stack of GLN torsors, or principal GLN bundles. But if I have a vector bundle over the scheme T, I map it to the isomorphisms of vector bundles from E. Well, so U is just a point, so T times U is T. So this is just E itself. Let me not write that. This is the trivial bundle on T times the point, so trivial bundle, so Cn on T.
Basically assuming that isom Yx is always representable there, what ensures that?
Yeah, well, you also have to prove that. This is look at this example. This is the frame bundle of E, which is a principal bundle for GLN. So you prove that it is representable because it's locally trivial and it's locally just a copy of GLN. Same proof works up there, just more language.
Can you explain what role smoothness is playing in all of this?
Good point. Let me just finish my sentence here. Okay, so this is, anyway, so, and then this theorem here is the well-known fact that, well, vector bundles and principal bundles are the same, right, via this frame bundle construction. I think actually you're right. This, for the validity of this theorem, for the definition of this thing, I didn't need smoothness. I don't think, I have to think about it again, but I don't think we actually need. I mean, for this theorem, for the theorem, we probably don't need this. I don't think. The thing is, if the, so because of the next definition, well, which looks a little bit different than what I said last time, so, So the stack X is an algebraic stack if there exists complete versal family. So in other words, then I can apply this theorem, and then I get that this stack is actually just isomorphic to one of these concrete stacks of torsors. And I'm never going to use this theorem unless I have a versal family, so that's why I stuck it in the statement. But I don't strictly need it. I don't think I really need it for the statement, for the truth. Yeah.
Why the smoothness for the constructed algebra? Same question as before.
It's just, yeah. To do geometry with these things, we need smoothness to get things to work. Yeah, can't see. Oh, just let me. Okay, so I just wanted to remark. So this we get. Because I've made this assumption that I only allow, I mean, I always assume that the symmetry groupoid of the family has to have this quasi-affine diagonal. And so again, you can, if you're willing to work from the beginning with algebraic spaces, you can relax this condition, and then you get more general kind of stacks, or more general kind of algebraic stacks. But this way we get algebraic stacks with quasi-affine diagonal, and that's a very large class. So that includes all Deligne-Mumford stacks and lots of Artin stacks.
In the last example, can you say how you see that GLN to a point is the symmetry groupoid for that family?
Well, you have to prove that this is a Cartesian diagram of stacks. So in other words, if you have a point here and a point there, which that's nothing, right? Just, I mean, a morphism to a point is no information. Then, so these triples are actually just, the x and y is no information. It's only the phi. So it's only isomorphisms phi from Cn to Cn. Sorry, because the image of the point here is that trivial vector bundle Cn. So that all the triples are just isomorphisms from Cn to Cn, which are elements of GLN. So last time I had introduced the Weierstrass family of elliptic curves, or degenerate elliptic curves. And the Weierstrass family, because of Weierstrass family, which is versal, because the symmetry groupoid is a transformation groupoid, and complete, because if you have a family of degenerate elliptic curves, you can always locally put it into Weierstrass form. Not globally, but locally you can. And by this theorem, I see that this stack, in fact, is then, well, as I said, it is a stack, right? Families of elliptic curves are local, so this theorem applies. I see that this stack of elliptic curves is isomorphic to to this stack of torsors associated to this groupoid of the action of C star on affine space minus the origin. And this is, by definition, the projective, the weighted projective stack with weights 4, 6. Because this were the weights of the action. So we see that this algebraic stack of elliptic curves is the weighted projective stack for 6. And in particular, a family of elliptic curves. So a family of elliptic curves, so ET with a section P is really, the same thing as a torsor for this groupoid, meaning, some C star bundle and an equivariant map to C2 minus the origin. That's really the same thing as a family of elliptic curves. Of course, there's always many versal families for the same stack. So, especially for a stack of elliptic curves that's been studied so much, many people have come up with nice families. So, let's just talk about elliptic curves, not degenerate ones, maybe. So this parameterizes a family of elliptic curves. But this is not algebraic. To talk about this, we have to go into the analytic category. So analytic spaces. This describes the family. And what is a symmetry groupoid? Well, again, because these are all nice families, the symmetry groupoid is very symmetric, and it's the transformation groupoid. Or another one, the Legendre family. You can figure out what the symmetry groupoid is. And so you can see that the main thing to prove that a stack is algebraic is to find versal families. So the question is, how do you find versal families? In general, often you can find versal families by rigidifying. So so for example, if you study elliptic curves, so there's a curve of genus 1 with a base point and a differential. So So with a global differential omega nowhere vanishing, the moduli space of such triples, so this is so. I don't know, I call this WC2 minus the discriminant. Throw out the locus where the Weierstrass curve is not smooth. So points in C2 minus the discriminant correspond canonically bijectively to such triples. So if I rigidify elliptic curves by introducing the differential, then I get this nice versal family. And I can see the choice of the extra datum, the extra differential, is unique up to C star, and that's why the symmetry groupoid is just given by C star action.
I'm still thinking, why do you need versality in your theorem and definition? So, is it correct to say that U is the atlas Fourier stack, and somehow, I think it goes back to what it means, the symmetry groupoid being smooth, right? I mean, those two maps should be smooth. So somehow you want to say that locally you can glue atlases to each other. Is that why?
Well,
I'm trying to say, even for a singular Artemis stack, you still need the smoothness of the groupoid because it gives you gluing of local atlases.
so let me. Maybe I'll try to say one thing. I don't know if this makes it much clearer, but so let me emphasize this analogy here. Analogy. So if between schemes and stacks. So here's a scheme. So X is a scheme, and say U alpha is an affine open cover, or maybe an étale cover, then the scheme is actually equal to the disjoint union of all the affine opens, modded out by the equivalence relation given by by the overlaps. So if you really want to work with schemes, prove things about schemes, you usually have to pass to some open cover and study the affine opens. You want to reflect, the fact that you want the geometry of X to reflect it as well as possible with these U alpha. So, so if these maps are actually Zariski open inclusions, then that corresponds very nice. If you work with étale, then U alpha still reflects the local geometry of X very well. But if you try to work with more general kind of covers, things will get more and more murky. But this, you want this to be the cover to reflect the geometry of X as well as possible. If X is an algebraic stack, with the replacement for these affine open covers is are these complete versal families. And then, as we've seen, then the stack is given as explicitly as U r, which I can also think of as the quotient of the groupoid, because right here I had this kind of diagram. Which now turns into this diagram here. And so these maps are smooth, which means that these maps are smooth. I mean, they're smooth epimorphisms. And again, to reflect the geometry of X and U, you want this to be as nice as possible. And smooth is just, I mean, the nicest general property. I mean, you would like to, if you can get away with étale here, just like in the scheme case, then your stack is actually a Deligne-Mumford stack. But to get more general kind of stacks, you have to relax the étaleness or the open immersionness as little as possible, and that's given by smoothness. I mean, you could try to work with more general kinds of groupoids. For example, I mean, I don't think you need at least, you're going to at least have to work with flat ones to get any kind of descent theory working. But there's a theorem by Artin that says if you have a flat groupoid, you can also construct a smooth one. So you might as well work with smooth ones for the definition. All right, so I just want to emphasize, it's really, you should think of these groupoid representations of the stacks as analogs of these. I mean, this is a special case, of course, of that one. This is the correct generalization to stacks. I guess I'm out of time, so I'll finish here.